environment from theory to practical applications. Today we are in the day 6 of this event, and now before we begin, let me introduce myself again. My name is Indra Gunawan from Geophysical Engineering ITB. I am the chairman of, and let me remind you one thing again, that this event is organized, be partnered with some university in the world, and this event is coordinated by Dr. Wahyudi from Geophysical Engineering ITB. This afternoon, at this session, joining us today is an expert from Kyoto University, Professor Katsuaki Koike. I will read some brief from. This is the profile of Koike Sensei. And today he will talk about radon survey for geothermal prospecting and active fault monitoring. He is the brief profile of Koike Sensei. He is the full professor in Department of Urban Management University, and in the research guide we found that he is already done 200 publications with more than 2,000. And his expertise in engineering geology, groundwater, remote sensing, hydrogeology, fractal analysis, inversion, and many more. And let's welcome Professor Koike. And Koike Sensei, it's so good to have you here. Thank you so much for joining us. And now let's ask Koike Sensei. You have about 50 minutes to your lecture and following with 20 minutes of discussion. And you allowed to extend your class as long as it's not more than 3 p.m. Indonesia. Okay, please. You might start your class. Koike Sensei, we can. You did not open. Yes.
Okay, I'm sorry. My mic was mute. Can you see my slide on the screen?
Yes, we can see it clearly.
Thank you very much for the nice introductions. My name is Katsuaki Koike, professor of Kyoto University. Thank you very much for inviting me to be very good opportunity for the class to ITB, the excellent student. So I'm sorry that I misunderstand that I have the 2-hour classes. That's why I prepared the many slides over than the 60. But I realized that my presentations or lectures is just 1 hour. So yes, due to the restrictions of the lecture time, at first I would like to introduce the several the topics of this radon survey for geothermal prospecting and the active fault monitoring. But I guess that I cannot complete to present these content just 1 hour. So if you have enough time, and if you allowed me to continue to my lectures, I wish to continue after 3 o'clock. No, I'm sorry, 1 hour. So this is the agenda of my lectures. At first, the self-introductions and fundamental of radon and the measurement method. And these are 3 applications. That is a main part of my lectures. At first, as shown in this title, I prepare the radon applications for geothermal reservoir characterizations. And the two topics for the active fault the monitoring, especially I want to focus on the relationship between seismicity and radon concentrations. So at first, I would like to introduce my university. Just a few, several minutes. My university, Kyoto University, is located in Kyoto City, the western part of Japan. And I hope many of you know that Kyoto is the old capital of Japan. So that this place is had been the functions of the government centers for more than 1,000 years. But now the capital of Japan is Tokyo. Kyoto University is second oldest, the Japanese university. And there are several campuses, the main campus located in downtown of Kyoto. But my campus for the graduate school of engineering is located in the western part of Kyoto and located in the hillside. If you visit to my campus, you can see the scenery of downtown of Kyoto, and Kyoto is the basin, the structures. So you can see that interesting the natural landscape. And my laboratory, there are several ITB, the graduate, and your colleagues. The one of interdisciplinary, the laboratory between science and engineering. Of course, we belong to the graduate of School of Engineering, but the many graduates that have a background of the science. For example, the ITB graduate that come from Faculty of Science, and some of ITB graduate come from engineering. So this is one of the biggest laboratory in the graduate school of engineering. That we have the 4 staff, including the associate professor, assistant professor, the postdoc researchers from the Brazil and the Canada and the ITB and the doctor course student and master course student. And our target is surface to the deep part of the Earth. And we are trying to analysis of multi-scaling from very small the structures of rocks to the wide scale, including for the systems and the fracture system. And we collaborate with many the disciplines in our sciences. For example, economic geology, the engineering geology, as introduced me, and geothermics, and remote sensing, and the geophysics, geochemistry. So even though just one laboratory, but we published the many several papers in the wide fields in geosciences, such as geochemical explorations and geophysics and remote sensing of environment. Our research policy is composed of data analysis, computer simulations, and also laboratory experiment, the field survey and the measurement. By combining these method and the field surveys, we wish to understand the mechanism of the Earth phenomena. And we want to construct the new hypothesis and the theory. And of course, we want to contribute to the innovative technology and the society. The field survey is a main, the core of our laboratory, including the geothermal survey. This is 1 year wind, and the groundwater survey in Africa, and this is the core survey in Indonesia, Belau. For the remote sensing analysis, we went to several places for the ground truthing. One is the Mozambique in Africa, but this was a survey for the groundwater potential mapping. At first, we evaluate groundwater potentiality by the analysis of satellite images by delineating fractures and vegetation areas. And the next, we went to the actual target areas to make sure that the resistivity structures, the groundwater, that is really the exists or not. And this is the mineral mapping ground truth in cuprite or gold field in America. So the main topics is remote sensing for clarifying the environment and the geosphere structures, and the geomathematics modeling of geosphere, the environment, and the applied geophysics and geochemistry for integrating imaging of geological structures that related to these three main topics that we published the papers in these journals. And this is one the examples of our outcomes. The one is the remote sensing, one is the detection of thermal anomaly, and this is a detailed mineral mapping using the usual the multispectral data and the hyperspectral image data. And this collaborated research with ITB, a new vegetation index for detecting the metal-induced vegetation anomalies. We published papers, the remote sensing of environment, and AGU journal. And also, we published papers in IEEE journals estimating surface materials and physical properties from the polarimetric synthetic aperture radar data. And one of the main our target is the hydraulic structures and the fracture systems. And today's main topics is this one, geochemistry, and the calculations of radon, gas from active fault, the geothermal reservoirs, and the rock fracturing. So that is our strong collaborators at ITB. And also the one of our the main topics is geostatistical or grade modeling of mineral deposit. So from this October, the female ITP graduate that will be a student of laboratory, that she will study about applications of geostatistics for the mineral deposit and hydrothermal the resources. Finally, fluid modeling by geochemical geophysics, geostatistics, and simulation method. But this one and this one's are related with each other in terms of the fluid flow estimations and simulations in the crust. So from 2014, we have strong collaborations with ITB for international project of geothermal enhancement use. So we say this project is Bagus project, supported by the JICA and the JST. And from the last year, we moved to the new project, now also supported by JST, but the target areas is now Patuha. So we will do the drilling survey to make sure actual potentiality of geothermal resources. So okay. So from this one's we are going to the main topics of these lectures. So at first, I will explain the background of radon research. And of course, many of you already what is radon and how is radon applicable to your field in geophysics. So the main functions of radon is a very good sensors of the cluster deformations, because radon constellations is very, very sensitive to the cluster deformations, for example, the strain accumulations and the fracturing. So why the radon is so sensitive to fracturing and the cluster deformations? Of course, due to the increase of the cluster strain, the several phenomena occurs. The one is increase in pore pressures, And with the increase in pore pressures, and of course, groundwater move and the gas move. So due to with the movement of the groundwaters and the geothermal fluid and gas, the radon migrate. So the one example is here is showing a relationship between the magnitude of the earthquakes and the phenomena about the hydraulic changes. So you can see that this is the hydraulic change. And for example, the groundwater wells and the stream the flows. It means that the groundwater level change associated with the earthquakes. So, but there are several phenomena. For example, core seismic change, or cursory change, and aftershock change. So anyway, you can see that the many change occurred. And of course, at the large energies larger than the magnitude 5, like that. And also this figure, a little bit old, but very nice pictures about relationship between the magnitude of earthquakes and the radon anomalies, radon change. So you can see that even though the small magnitude, such as magnitude 3, 4, if the location is near the epicenter, the radon, the change and the observed like that. But of course, with increase in the magnitude, the far away, even though the far away, the radon change, radon anomaly are observed like that. Even though the epicenter, the distance is 1,000 kilometers, but there are the observations of radon anomaly, for the magnitude 7. So the one like that. So one example is in the such a hydraulic change. Recently, about 5 years ago, there was a big earthquakes in Kumamoto area in the western part of Japan. The earthquakes that occurred this date, the 14th April. You can see that the core seismic change in the groundwater level. The groundwater level suddenly drop like that. And the interesting features is that the groundwater level gradually decrease like that, and then suddenly drop by the ruptures, fractures. So it means that these areas, the strain, the increase, with the increase of the compression, the stress. So this, of course, that has a change in pore pressures, and that is pressure change and the release of the pressures and the rush of gas or groundwaters that carry the radon gas near the ground surface. So today's the main topics of my lectures is like that. What are the chemical and physical features of radon, and where and how does radon come from and to the ground surface, and what are main control factors of the radon concentrations, what subsurface features that can we estimate from radon concentrations, what are merit and the limitations of radon applications. Of course, there are many the geophysical method, geochemical method. Radon is just one the method of geophysical, geochemical method. There are many other methods are very effective. But what is the merit of radon? And what are the next radon researches that may be for you and for our laboratory. So this figure is a very fundamental. The physics of radioactive decay. yeah, you already learned this figure at the bachelor level of physical or chemical class. There are three the typical decay styles of the radioactive nuclide. One is alpha decay, beta decay, and gamma decay. So for our geophysics, usually we use the alpha decay and the gamma decay. The alpha decay, helium, the nucleus, this one is the emitted, is like that. So the beta decay is emission of electrons or positive electrons. And the gamma decay is the largest energy, the emissions of high electromagnetic wave as a form of photon. So the radon has a decay of this style, alpha decay, and emits the alpha particles. So of course, the gamma decay is useful for our geological survey and the geophysics. For example, this is the airborne, the radioactive, the survey, using gamma ray is examples. So for the gamma decay, the target radionuclides is the uranium, thorium, and potassium, here like that. And this is effective for the regional survey because we don't need to survey on ground. Such gamma spectrometers in the carried on the helicopter or maybe drone for the extensive survey. And this method has been widely used for the geological mapping for the areas which are very difficult to access, such as glacial areas or desert areas or deeply vegetated areas. Why this method is effective for geological mapping? Because each rock type has different composition ratios of uran, thorium, and potassium. Of course, the granitic rocks that had the largest content of these radioactive nucleus, but the other, for example, basaltic rocks, the content of this uranium and thorium is low, but it has contents of potassium. And by the ratio, the relationship of these three radioactive nuclides, for example, these materials, the nuclide, the all high, or these rocks is just potassium is high, and these rocks just the uranium the high. These rocks is only thorium is high. By using such the features of rocks depending on these three radioactive nucleus, that we can know the types of rocks. And this is very successful area, the examples of the geological mapping, the covering the all Australia. That you can see very clearly the difference in color. And of course, this difference in color is a difference of compositions of three radioactive nucleus, and resultantly, the difference in the rock type. Of course, these techniques is useful to locate the uranium deposit. Of course, there is a uranium deposit that we can see, we can know, we can measure the high the uranium, the gamma ray intensity coming from the uranium. Okay, so we are going to the very basic the measurement of radon. So at first, I'm sorry. About 1 hour ago, I sent you a PowerPoint, the PDF of this my handout. But there are several mistakes. One is this one. So this is the uranium series, and this is the thorium series. The parent of uranium series is this uranium 238, but in thorium series, the parent is 232, the thorium, and this is half-life is a little bit different. I'm sorry. Please correct my handout to this one. So the what radon, type of radon, isotope radon, are used for radon survey. The radon has several isotopes. The isotopes, typically the radon and the thorium, 222 radon and 220, we say that this is radon and this is thorium, are used. But this is the half-life. So both has the decay type of the alpha, and both are daughters of the radium. The radium also has the decay of alpha, like that. The difference is half-life. As you know, the half-life time, that means the times that to take the half of the number of the radon atoms. The radon, the half-life is the almost 4 days, but the thorium is a very, very short half-life. It's just the 1 minute. The why we can use radon, because this are the fundamental features of radon. The one is the radon is chemically inert. So there is no, for example, oxide radon or hydroxy radon. The radon is radon. So radon is chemically inert and not organic. So in other geochemical prospecting, some papers use carbon dioxide. So there are two sources of carbon dioxide, inorganic and organic. So even though we measure high carbon oxide concentrations in the topsoils, it is very difficult to discriminate the source of carbon dioxide coming from, for example, bacteria or a plant, decay plant, or the deep terrestrial gas. But the radon source is not organic. And through focus on my colleague, very, very excellent co-workers in IDB, use this radon for the spring waters of active fault areas or geothermal areas. Naturally, the occurring as a radioactive gas, and the important thing is can be detected at the extremely low constellations. So even though in ITB campus, if you measure the radon concentrations, that you can measure a little bit the radon the concentrations. So the usual case, there are 3 types of the radon measurement. So most traditional is the radon, the alpha scintillation counter. So we pump up radon gas, and we use the cell coated by scintillator. This cell is coated by the sulfide, sulfide zinc, mixed with the silver. So the fen radon, radon, emit alpha particles. Alpha particles, of course, attach reach the wall of this cell, and by the scintillation effect, with the interactions, alpha particle, and the light. So this the sensor can count the number of how many light measured in a short time. So this this equations is a little bit old. That we published the papers about how we can calculate correctly the radon concentrations for this alpha scintillation counter method. So this method, the little bit out of date, but very the interesting or important to consider the essential features of radon. Because we found that there are two types of radon gas using by the many case studies in Japan. The one case is the radon concentrations increase with time, like that. And the second type is radon concentrations decrease with time, like that. The most studies that don't consider the difference is radon, because most the studies measure just a few minutes for the starting of measurement, and just 3 minutes or 5 minutes. Okay, that we can get good data of radon, but we try to measure for a long time, over than 10 minutes or 20 minutes, and found very interesting features. And we could understand that this type shows non-equilibrium conditions. This means the radon that is very the soil gas or terrestrial gas is very young. So this gas means the relationship between radon and its daughter polonium has not reached equilibrium conditions. So the usual case, the radon concentrations drop within first few minutes and takes stable like that. This means that equilibrium conditions, the gas is old. That's why the radon and its daughter polonium, this one, this is daughter radon, and its parent radium, radon, and polonium. The stable equilibrium. So it means that the number of decays of radon and the number of decay takes a constant ratio, always a constant ratio. So this thick line shows the theoretical curve based on the two equations. They're not so difficult. Just we consider the radon decay law and such equilibrium conditions. And the difference is the gradient within the short near the start of measurement. So for example, this is a gradient is steep. So it means that non-equilibrium conditions continues for a while. But this one is the gradually the approach equilibrium conditions. So it means that this this is the youngest gas. And sometimes we encounter the mixtures of equilibrium and non-equilibrium conditions. Now, next one is the also traditional method, the ionization, the chamber method. So it uses the phenomena of strong ionizations of radon, because as I said, radon emit alpha particles. So when the molecules receive attacked by alpha particles, these molecules occurs the ionization like that. this method, what is the difference of this method and this method? This method is effective, useful for the long-term radon measurement. This method is point-by-point the radon measurement, because that first we drill a hole and we pump up the soil gas or terrestrial gas from the duct hole. So for this case, once we drill a hole, and after that, we continuously pump up gas like that. This is a sensor of this ionization chambers. So this chamber or sensor continuously the temperature change in the radon measurement. So the final one, I'm sorry, I don't prepare the slide. The latest one is this one. So this machine is also prepared, equipped at the department, your colleagues at the mining department, or petroleum and mining department. So there this the difference of energy, the alpha particles. So the similar to the gamma ray, there are several the energies in the alpha particles emitted from the radioactive nuclei. For example, the energies of the polonium, energies of the bismuth, energies of thorium, they are different. So difference of energy that we can discriminate over the type of the radioactive nuclide. So this is the latest machine that using the energy of alpha particles. So the first topic is the temporal spatial change in radon constellations for geothermal reservoir characteristics. As in my title, this is the first study of geothermal study. So the radon, the background is radon is mobile in the volcanic hydrothermal systems. There have been many several papers about applications of radon in geothermal reservoir characterizations or volcanic seismicity. But the issues still remain about the response of radon to the reservoir, the thermodynamics, the fracture systems, and seismicity. We published papers, these topics in 2014 JBGR. So before that, of course, there are many papers, but we thought the systematic radon measurement for targeting for a long time and focusing on the reservoir temperatures or seismicities are not so many. That's why we challenge it to clarify and unravel such phenomena for the development of geothermal studies using radon. So the purpose is to correlate radon constellations in detail with the volcanic seismicity and correlate the radon constellations with the reservoir temperatures and pressure change. Maybe this one is a first study. And we want to unravel and clarify the mechanism of radon change, and we use to identify and control factors. So this, the radon survey, of course, the good the test field necessary, the preferable. So we selected the most typical geothermal area in Japan, in southern South Japan here, because before moving to Kyoto University, I spent 20 years in these Kumamoto areas, and your ITB colleagues, the 3 colleagues graduate my laboratory in Kumamoto University. Mount Aso is the largest caldera in Japan, about 40 kilometer. In the center of the caldera, there is the active humerus, the craters, Aso crater. And in the western part of Aso craters, there are three main hot springs and the surface manifestations. Also, the area, Kyushu area, is famous. The places for the rich in geothermal resources because of many active volcanoes and hot springs like that. In Japan, of course, Indonesia has much larger electric capacity than Japan. In Japan, the largest electric power stations is located in this one. Hachowa power stations, but it's just 110 the megawatt. This is just half of the 1 year wind geothermal power station. The scenery of each hot spring is like that. So you will have lectures of the electromagnetic surveys by Professor Goto. Goto Sensei, he is my colleague, and he was associate professor at my laboratory, but now he is professor at Hyogo Prefecture University. We also conducted the MT survey, the magnetic survey in this Aso areas. And we found two reservoirs in these three hot springs. The one is here, the one is here, and this blue the shape shows the cap rocks. And what is this green line? The green line is the result of numerical simulations and showing the temperatures at 180 degrees in Celsius. So you can see very good agreement between the location of reservoir like that, and also the high temperature zones like a mountain. The one interesting feature is that this area has a shallow reservoir, much shallower than this reservoir, like that, here. So this is the result of the temperature change of radon constellations, volcanic seismicity for 12.5 years. But maybe before these papers, this was the longest radon measurement at the target, the fixed areas. And because we wanted to get the very reliable radon constellation data. This is a time and about 13 years. And the bottom figure shows the seismic intensity. So you can see like a spike like that here. That spike shows the high seismic activity in the volcanic regions. And this one is the radon constellations. And this the red curves shows the smooth the radon constellations, because the original radon constellations like very fluctuated. We want to know the general trend of radon constellations. That's why we apply such a smoothing of radon constellation data. One interesting feature is the radon constellations, the increase abruptly with the increase of seismicity. Of course, the seismicity is not continuous, it's like intermittent. So for example, this is very quiet, the time, but suddenly the seismicity became active like that. So in the very harmonious with the increase in seismicity, the radon constellations abruptly, the increase is like that here. And the one interesting feature is quite the non-active the seismicity period continues almost 1 year, and in this quiet the period, this the very the occasionally seismicity increase like that, like a peak here. There also here this is a good correspondence. The radon concentrations, the increase is like that. So maybe this is the first very systematic result that showing good the correspondence agreement, good response of the radon concentrations and the seismicity, the proved by very long measurement period. So sorry, the order is reversible. The interstices of the abrupt spike-like the increases, this seismicity that have a abrupt spike-like increase. So one remarkable features is that these spikes they correspond well with the local the maxima of radon concentrations, the common to these 3 sites. And we are using this the theoretical the equations that we can calculate the radon gas. So how times has the lapsed from the birth of this gas? This means that this very young gas, and this is old gas. This the very old gas that because it reached already equilibrium conditions, but this is very young. So we want to calculate the how is young, the how time the takes after the birth of the gas. So this the calculated the gas age. So it means that this is young. That this the directions become young, and inversely this is all the directions. So interesting features. The when radon concentrations increase here, the gas age they become younger, and the radon concentrations decrease. The general trend is gas becomes old like that, and young. And the interesting features from here to here, the radon concentrations increased for a general trend like that. The following these general features, the radon gas that becomes young like that, and also the radon gas radon concentrations decrease from this maxima toward the end of measurement. The agreement with this trend, the radon gas, but generally they're getting old like that. So this became young and old. The commonly that we observed at 3 our study areas. So here, the common to 3 sites radon concentrations that has a general trend up, low, up, low, up, low, up, low. And the gas age have a sudden the conspicuous increase like that. And the age spikes they corresponded. This one very young, very young. And this one is a very this one is a very here very young. So this maximum or radon concentrations and gas of the gas age is correspond agreeable. That is matter of course. The why radon gas increase, of course the gas volume that becomes large. The much radon that this gas carries. That's why radon concentrations increase. But this trend that we observed, the very the long term the observations, because even though it seems many data, but this measurement occurred just one time in a week. So it means that this data we got 1 week intervals. We don't know the more details, the change, the temperature change or random constellations. To compensate this long term, the trend, to know the more details, temperature change in radon, that we measure the continuous radon constellations using these systems here, the ionization chamber method. So this method continued about 2.5 years. So this is a limit or measurement, because the usual case these machines is not effective for the radon concentrations in such a high humidity and high temperatures. In particular, the high sulfur content that destroyed sometimes the sensors of machine. So there is the drop, there is the stop for measurement. This is because our machines are broken. For this broken, we paid much money to repair the sensor. So that's why we take much effort to get these data. This figure shows the continuous constellations are not continuous. Sometimes there is a stop, lags in measurement because of the broken of sensors. The line shows the radon constellations, and this one is the temperatures. So at a glance, you can know that there is the reversal, the relationship between radon and constellations. Radon high, but the temperature low, like that. So this general trend appearance can be confirmed by the scattergram between atmospheric temperatures and radon concentrations. So this relationship is different with the period, because the summer period, winter period, the trend is different. But generally, there is a negative trend. Radon concentrations the increase with decreasing in the cold environment. That maybe this is a condensed the effect of condensed waters, we think. So that we cannot use directly the radon constellations, because such a temperature informations and water content informations are included in radon constellation. That's why at first we deleted this effect of weather conditions, temperature, and humidity. And the rest of the radon constellations, we say this is a residual of radon were used for the next step. So this red shows the radon constellations that removed for the temporal and the water humidity, the effect. So you can see the temperature change, radon constellations clearly the increase, decrease, increase, decrease, and increase like that. There is the long periodicity in the general trend in radon constellations, similar to such a very long observations for the 12.5 years. So for long-term period, there is a trend. And the short-time period, there are also the trend, general trend. And at first, we think that this general trend was made by Earth tide. Yeah, here, this total tide. The blue line shows a total the Earth tide. That we can calculate very easily Earth tide, like that. So this is the tension or compressions. So that you know that Earth tide has a very clear the periodicity, half day and 1 day. And the at glance, the radon concentrations and the Earth tide has correlated. For example, the radon concentrations increase, with increase Earth tide is like that, but the correlation is not so strong. And one more thing is the periodicity is not different. So there is no 1 day or one half-day period included in radon concentrations. That's why that we consider that, of course, that there may be an effect of Earth tide in our radon measurement, but there must be the larger effect included in radon concentrations. So that's why we want to specify what are the larger effect than Earth tide. Now, of course, based on our long-term radon measurement, we firstly consider the effect of seismicity. So this correlation is much precise than the before, because the before is 1 week the correlations, but this is the continuous radon concentrations. And this seismic instasis is summarized or accumulated 1 week. So you can see that the radon concentrations are similar to the long-term observations that has fluctuated, large and drop, and that this increase the more clearly than the just 1 week, just a one-time 1 week the measurement. And the one interesting features is that this one, that there is the good correspondence, the agreement of the seismicity and the local maxima of radon concentrations. So the seismicity that became active, the radon concentrations they also increase. So one more important thing is there is a time lag between the seismicity and the increase in radon concentrations. How is the time lag? The time lag is the variable, the case by case, but the usual case, the same date to the longest, the 25 days, but mostly 10 days time lag. So we could understand that the volcanic seismicity occurred that may be several kilometers below from the ground surface, and this effect appear that takes by taking 1 week or 2 weeks appear in the soil gas, the chemistry near the ground surface, just we dug holes with a depth 1.5 meter. And next one, but unfortunately, the radon concentrations cannot give us the information of temperature. That's why in parallel with radon measurement, we measure the several gas components. For example, methane, methane, the carbon dioxide, and helium, and hydrogen, like that. So using the traditional the geothermometers, we calculate the reservoir temperatures using equations of gas thermometer. This figure shows the resultant, the temperatures, reservoir temperatures, and radon concentrations is like that. And this is a scattergram between calculated temperature and the radon gas concentrations. So even though the correlations is not so high, that we hope the stronger correlations, but just the 0.5 the linear correlations coefficient. But it is indeed the radon concentrations increase with increasing in reservoir temperatures, and based on these geothermometers, the estimated temperatures in the reservoir vary from 2 30 to 285 degrees in Celsius, but the average is 265 degrees in Celsius. So it means that, of course, the radon concentration is changeable with seismicity, and the which is first, seismicity or the change in the reservoir temperatures, the which is first or radars. But we don't know the which is first, but it indeed the seismicity affect the change in pressure and the temperatures of reservoir. So using by making several empirical equations, we estimated reservoir temperatures in other two areas. Here. So this 2.5 years continuous measurement was carried out at the GEOC site here. So even though the different places, the general trend of the radon concentrations and the reservoir temperatures are similar, like that. For example, the reservoir temperatures that decrease. The reservoirs, but the peak of the radon, the reservoir temperatures or drop of reservoir temperatures, the similar period. So the discussions about why radon concentrations are affected by the reservoir conditions are described in my papers in JVGR 2014. But the summary that I thought there are 4 factors strongly affect radon concentrations in the near surface. The one is, of course, this one is ascent flow. With the increase of reservoir temperatures and the seismicity, of course, the volume of gas becomes large. This volume of gas carry the radon gas much. And the second one is this gas velocity, the increase. So I will show you more details about the advective, the diffusive equations of radon transport. And this the radon gas velocity had the strongest effect on radon concentrations. So the third one may be this the boiling point that may be changed with the change in reservoir temperatures. The boiling point that may be changeable up and down, depending on the reservoir temperatures. And the fourth one is, but this is questionable. And in addition to the gas velocity, there may be the diffusive effect, a diffusive coefficient of radon that may be large. So it is known that the diffusive, the molecular diffusive coefficient of radon is very small. But we apply advective diffusive equations that with the increase of the advective velocity, it means the carrier gas velocity, there may be diffusive coefficient that will be increased. So maybe such 4 interactions, the radon concentrations, that may be the increase. That this is my interpretations for the first this case study. So this is just I must hurry. This is ongoing research with the ITB, excellent colleagues. As I said, we have the carrying out international geothermal the project for targeting Wanya wind and Patuha. So that we want to enhance geothermal resource use for power generations. For this case, the radon measurement is one core of this project. So that we want to know where is the good places for production of wells for power generations. So we have carried out the systematic survey, including remote sensing, geochemistry, geophysics, and computer simulation. And of course, the target one-year wind, PAPHA. And at first we detected and 3D simulations of fractures in one-year wind, and the targeting high fracture zones that we made the shallow drill holes with a depth of 5 meter depth, 5 meter. And this is a systematic measurement monitoring point of radon. And we use the latest radon machines, but this machine shows the same trend with our very old the alpha scintillation counter method. There is two types of radon constellations. One is that this is non-equilibrium conditions. This is equilibrium conditions. So this the non-equilibrium patterns that observed that this one is the intersections of the fractures fault like this, and also this is by the remote sensing analysis we could detect alteration mineral distributions by the analysis of satellite images. These distributions are kaolinite. So maybe these are good places for making production wells because high potentiality of the geothermal resources because radon gas large, and also there is the surface manifestations of the hydrothermal alteration. And but one point is radon measurement is point by point, so it cannot know the continuous the constellations to the supply the interval point informations. We combine lineament analysis detected from satellite image or this elevation model and using and co-clicking method. So this is the final result made by our colleague Professor Heriawan. And this one is the point of showing equilibrium conditions with high radon concentrations. And also that we could detect very high potential zones of geothermal resource in the southern part of one-year wind. So, and the why, that this is just the support of this idea that we calculate very simple the calculations that in this case there is no carrier gas provisions. So for example, there is no gas flow. For this case, the radon gas shows the decrease with the time, but the point is always supplied by the carrier gas. Radon concentrations increase and shows stable patterns. And this radon gas path is now demonstrated by such electromagnetic survey showing the resistivity structures. Okay, so I hurry to second or third topics, but second and third topics are not so many slides. So second one, the topics is changed to active fault the zones. So for the active fault zones, also there have been many radon applications to find out fault locations and to find out relationship between radon concentrations and the seismicity. But still, the uncertainty progress because not always the radon concentrations increase at fault locations, and not always radon concentrations increase with the time of earthquakes. So that's why we want to know the most rational cause of radon concentrations. And we want to discriminate the always active, the always moving the fault, and the not active fault. So this one is a fault that experiencing stationary fracturing at short time, or a fault experiencing intermittent intermittent large fracturing over long time intervals. So this is published in this paper. You can, this is open access journal, you can download freely. So for this, this is also that we that took very great effort by selecting several active fault areas in Western Japan. It took about 10 years to complete the radon measurement, to publish just one paper. And these are very traditional, famous active fault in Japan. For example, in the central Japan, Totsugawa, Atla Fault, and this is Nojima Fault. And it has huge earthquakes in 1995. And in Kyushu areas, Hinagu, Futagawa, as showed you that there was earthquakes in 2016. And there is a normal fault that's surrounding the active volcano. So this is one snapshot of the field scenery of the measurement of radon in the plain areas and mountainous area. And 2016, 5 years ago, there was two huge earthquakes successively here. And there's a main shock, and this is a precursory shock, before shock, Futagawa, the Hinagu Fault. So before that, similar to the radon constellations in volcanic active volcano areas, that we measure the resistivity by MT survey and AMT survey for these two active fault areas. That is the main shock, that this is the before shock, precursory shock. And this figure shows the resistivity distributions. That this is conductive zones and this is resistive zones. And this the circle shows the small earthquakes. They're just the size, the magnitude, the lower than 1 or 2. It is interesting that the many earthquakes have been occurred in the low the resistivity areas. Is like that. And also, this figure shows very clearly the fracture zone structures of these Futagawa areas. You can see the cores, the center of fracturing of the active fault here, 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 here. The depth is about 5 kilometer depth, 10 kilometer depth. So, and also it is interesting that the earthquakes propagate shallower to the Mount Aso. And this trend is correspondence with the earthquakes occurred in 2016. And also, it is interesting that fracture zones that become shallower with the harmonious with the epicenters. The one interesting features we found is like that. So there's a very clear boundaries of the large resistivities and low resistivities. And a very important finding is the many earthquakes occurred at the boundary of high resistivities and low resistivities. It means the fracturing ruptures occurs between the conductive and the resistivity zones. It means that the rock stress, rock strain, that can be easily accumulated between such the different mechanical physical properties of rocks. Well, these two slides shows that the photos after the huge earthquakes 2015 taken by me. That we measure the radon constellations before these earthquakes. And you can see that the lateral slip, the right lateral slip, this Futagawa fault is like that, by the shape of paddy field like that. And you can see the ruptures of the road like that, and the collapse, the landslide like that. And the very surprising thing is that this one, the large, huge, the bridge was dropped like that. So it was very shocked for me. That this is because of the landslide of this mountain. The nugget of huge, the soils, rocks destroyed and drop the bridge to the bottom of river here. And the one more interesting features is that this is convenience store, that there are many cracks, fractures in front of this convenience store. These fractures, the directions is similar to or equal to the strike of the active fault, yeah, like that. So recently we published 2 papers in this journal, 2017 and 2020. And this paper shows that our interpretations was correct. So even though we gather all such MT data collaborating all Japanese universities, and we found the seismicity occurred between conductive zones and resistive zones here. So you can see the earthquakes that occurred, this one, for example, the yellow zones and the green zones. So here we could make sure that the strain and the stress can be easily accumulated, such as different contact zones of different rock properties. And that's why the earthquakes tend to be occurred, such accumulated strain stress zones. This is just the scene of the radon survey here like that. And the pre-shock of earthquakes occurred in this area. But of course, that we measure more than 10 years ago, before the earthquake. And in addition to the radon constellations, this mass, using the soil samples and the gamma ray survey. This is the Hinam fault. So it is very interesting that in addition to the radon constellations, but the other radionuclide shows anomalies at all the same locations here. So this is published in our papers 2009, that we to calculate numerically radon constellations using such a fault model. So when the fault deep like that, so the peak of radon constellations are biased from the center of the fault westward. Eastward. Sorry, this is center of fault, and the high radon constellations moved to the eastward, like that. And also the radon constellations shows a long tail is like that. It means that there is asymmetrically, not symmetrically, the radon constellation shape here. So we can easily estimate or predict that asymmetrical features must be occurred from the dipping of fault. So this was confirmed by such a very simple numerical simulation. And we consider that these features that may be related to the east dipping of the active fault is like that. So this is because this fault had the reversal type. So because of the east dipping, the radon constellations maybe show the anomaly in the eastern zones of the active fault. So based on this result, this is the examples of all the radon, in addition to radon, the other element show the higher content than the other areas. These areas not related to the active fault, and also the radon concentration shows the there is a seismicity. I'll show you just the seismicity. Sorry. This one is very important. And also important is that radon concentration shows non-equilibrium conditions, even though this is a usual soil. The usual soil is very similar to the soils in ITB. Apparently, there is no difference. But surprisingly, the soil gas shows the equilibrium, non-equilibrium conditions. It means that the radon gas is very young. So based on this result, we considered first that this is the stage of 2009, that the radon concentrations increase. There may be accumulations of parent atom in the shallow surface, because there is the photozones, and the photozones contained the gouge, the clay minerals. As you know, the clay minerals contains can absorb radioactive nuclide such as radium and thorium. So by the fracturing, the gas occurs from the deep part to shallow part, and radioactive nuclide accumulated in the clays, gouge in the photos fracture zones. So this accumulated the parent radionuclide may be the source of radon in the shallow surface. So, but this is the first idea. But we found that this is just one case. So some cases follow this phenomenon, but some cases doesn't follow. Why we think that this is just one special case, this one. So this is because based on the radioactive radon survey for the many active fault, 7 active fault areas in the Western Japan. So we calculate the relationship, the rock type, and the radon concentrations. Of course, granite has high content of radioactive nuclide. That's why the radon concentrations relatively higher than the other rock types. But and also this is the content of the radium, the parent of radon. So the granitic rocks, the higher content of radon parent than the other rock types. But here, however, difference is median values here of rock types very slight, but the radon concentrations very widely dispersed, the different between place and place. That's why we think that rock types is one indicator, the influence factors, but there must be more important influence factors. Because this figure shows the relationship between the radon concentrations and the parent radionuclide, the radium. So there is a very, very little the relationship of radon and its parent. But the correlations is just 0.517, and focusing on the very famous active fault areas in Attila here, the no correlation. That's why we apply this diffusion and advective and diffusion equations to find out strong influence factors of radon concentrations. So this equation is very, very simple, that we can get theoretical solutions from these advective and diffusive equations. Using these equations, at first we examine the effect of the gas velocity. And the second one is the effect of diffusion coefficient. But the diffusion coefficient effect is not so strong, but actually it has an effect. But this one, the gas velocity has much stronger the effect of the other parameters than the parent, the constellations of parent, constellation parent, the radionuclide, radium. For example, there is a 10 times difference of gas velocity. Here, this one is 5 times the difference of the gas velocity. Even though the same radioactive nuclide or parent atoms. So the radon constellations is 3.1 times higher. That's 2.3 times higher increase, even though the same constellations of parent atom. Yeah, that's why that the absence of that we consider that the absence of correlations that depends on the difference of gas velocity that carry the radon from deeper to the shallow depths. So the next one is that we want to know the relationship between seismicity and the radon constellations. So this idea is very simple. That this is, for example, this is a target area that we draw a circle within 100 kilometers, and we summarize, we integrate, we the summing up of magnitude of earthquakes included in the circle. So, and we say that this accumulated earthquakes energy is total earthquake energy. So this is the relationship between total earthquake energy and this radon constellations. So it seems very good, the correlations, that even though there is a wide the deviations or standard deviations of radon constellations. But you can see that the total earthquakes, it means that during 10 years, the many earthquakes occurred. So even though there is no large earthquakes, but some active fault always fractured. And this fracturing shows many micro earthquakes, not large earthquakes. So this one is occurred very earthquakes 1995, but actually the seismicity decrease after that. So for this case, the radon constellations does not increase. And this Atotsugawa is one of the most typical active fault in Japan. But this is historically earthquakes. About 10 years ago, the large, huge earthquakes occurred at Atotsugawa fault. But recently, the micro earthquake activity is not so high. So for this case, the radon constellations does not increase much. So this figure shows or teaches us that the important thing is the recent, the micro earthquake, recent seismicity for increase in radon constellations. So finally, for the topics 2 is the usual case in the shallow depths that we consider the Darcy law. It means the carrier gas velocity of radon that is small. And we assume the laminar, the flow of the carrier gas. And this laminar flow is governed by the pore pressure at the radon source depths. So this pore pressure is very sensitive to micro earthquakes, the recent micro earthquakes. So the increase in stress can enhance the pore pressure that induce an increase in carrier gas velocity and consequently an increase of radon concentrations. That's why from this lesson that we can understand that gas velocity is the essential factors. And this gas velocity is sensitive to pore pressure. And pore pressure is sensitive to the recent micro earthquakes. Now, of course, huge earthquakes makes influence much larger than the pore pressure. So the finally, just more than 10 minutes. Finally, that we want to understand natural phenomena by many field survey, but we want to know the actual, the true, the mechanism, the using that experimentally. So this is back the granted that the gas velocities and pore pressures and fracturing are the important essential factors. But we want to know that these were true or any other the influence factors for radon increase. So that's why we try to apply the rock, the fracturing test, very simple rock fracturing test that using, but we focus on the granitic rocks. Because granitic rocks, as I said, has high content of radioactive nuclide. So this one is published in JGI 2015. But in Japan, it is interesting that there are several granitic rocks, very beautiful granitic rocks, and with different particle size. So we sampled the granitic rocks in different age or different rock textures, or different in mineral textures or mineral compositions, like that. And this is polarizations photo, and this is parallel, and this is cross nickel, open nickel, and cross nickel photos that you can see that these rocks has a high the particle size, and this one is a small particle size. So this is the result of uniaxial compression test. This one is the stop of the loading because of the collapse or fracture of rocks. The stress, strain increase, and loading increase and loading stop by the collapse or fracturing of rocks, like that. So the common to all rock samples, the radon constellations are these radon constellations, and this is a compression stress. Yeah, compression stress. So you can see that the common to the rock samples, the common to the granitic rocks, the radon constellations increase suddenly after fractured, after fracturing. Yeah, like that, like that, like that. But some of rocks, the radon concentration increase after 50% of the fracturing, like that here, and also here, like that. And these rocks, the radon concentrations increase after fracturing. And one interesting, this is surprising result. There's no increase in radon concentrations for this rock, even though this is a very traditional, the granitic rocks in Japan. So these rocks is very expensive for the making a tomb. And we make correlations between the radium content of rock samples and radon concentrations. So it is very easily understand. For the previous cases, the source of radon may be located deep part. That's why the carrier gas velocity must be important to the carry radon, and also to control radon concentrations near the surface. But this one is we can measure directly the radon from the source, such a rupture plane. That's why there is a very strong correlations between radon concentrations and the parent radioactive nuclide like that. And also the findings by this experiment, there is a negative correlations between uniaxial the compression strength and the radon concentrations increase. So it means that here the compression strength is large, the radon concentrations is low. In other words, the compression strength is low, radon concentrations is high. So there is more interesting the negative features. So there are the several factors we examine, but more details, please read my papers if you are interested. So for example, we calculate the grain size by the microscope and the content of colored the minerals such as biotite, the hornblende, and this radioactive parent nuclide concentrations. And this is the uniaxial compressive strength like that, and the time to the failure here. So for example, this is very strong, and it takes much time for the rupture failure here. And the one important or interesting features is that there are, of course, there are, rock mechanics. There are two failure patterns. One is conjugate type, and this another one is tensile type. And this longitudinal the cracks and the conjugate here like that. Like that. Now this is the tensile cracks, or this is conjugate cracks and tensile cracks that you can see. And the stress level at radon increase start as compared to the compressive strength, such as 50%. And this one is interesting, 0%, no radon increase. So by integrating all informations that we consider that why radon concentration increase with the earthquakes. So some cases as I showed my first slide, that there are the phenomena of pre-earthquake response of radon observed. For example, there is two cases why the radon change, decline, and increase. So for the decline conditions is strong compressive areas, the stress conditions, and the crack conditions is close. And for the increase, of course, the dilatancy areas, the crack opens. And the pre-failure and the post the earthquakes, the responses, the radon change. There are two types, the large increase and small or no change. Of course, radionuclide content, the large, small. The grain size and small, large, and the failure progress velocity. This is high and low. It means that the failure progress very rapidly. And also the break failures, the heavy, the fragment for large, the emanations areas. It means that the failure areas extend largely. It means that radon emanations the occurs the effectively and actively. And of course, the combined with the previous case studies, the ascent gas velocity in shallow cluster high. In other words, contrary to it, that is small or no increase, the break patterns, the usual fragments, not so heavily fragment. the areas for the fracture planes are not so high. And the connections with previous research result, ascent gas velocity is low. That's why this is our interpretations or our conclusion. So this is general conclusions of the 3 topics to geothermal reservoir calculations. So the most important thing is like that. So the reservoir permeability can likely be enhanced by earthquakes as a result of the generation of features fractures. So this enhancement can cause increase the upflow fluid velocity, temperatures, and gas flux in the reservoir. This is a similar conclusion finding to the second and the third case studies. Now also, this is one-year wind case studies. This result can be applied to the one-year wind or patha in geothermal area in Indonesia. So the degassing of hydrothermal fluids is important factor. Active for the seismicity, the main result, here, the correlations between radon constellations and seismicity suggest this terrestrial gas is very sensitive to small change in strain, and this is not really not only can be said to the terrestrial gas. In my first slide, the groundwater level is also sensitive to such cluster deformations, cluster strain. And that's why both the hydrological phenomena and this gas phenomena are both important. Finally, this one is the case studies of rock fracturing. So the fracture patterns, conjugate shear, and the tensile types, the compressive strengths and grain size are possible control factors on the maximum quantity of radon emissions that induced by failure. Maybe this is the new the findings by our studies. And the one more additional findings: rock fracturing and failure do not necessarily induce increase in radon emissions due to the rock properties. That's why some areas not so good response to the precursory or aftershock or co-seismic response of radon constellations. Okay, terima kasih. Thank you very much for your kind attentions for my lectures. So I'm very happy if my lectures can help your understanding of gas geochemistry, in particular effectiveness of radon survey. So we have more than the 15 minutes for discussion. So if you have any questions, please don't hesitate to ask me. I have many chat questions. Oh, there are so many chat.
Thank you very much, Koike Sensei, for the explanation of the courses. And now we are enter to the discussion section.
Yeah.
So the participants can raise the hand if you want to ask Koike Sensei directly, or the participants can write down the question in the chat room. Maybe it is only one question from Dr. Wahyudi. It's a 3 question for you, Koike Sensei. You can answer the question.
Yeah, okay, thank you. Thank you very much for Professor Wahyudi. These are very detailed questions. So the letters are a little bit small. So some part so the last question is very simple to read. And how quick is radon gas emitted from subsurface? This is very important, and this is essential matters. So honestly speaking, we cannot estimate. So how we can know? There are 2 approaches. One is that we apply numerical simulations to estimate gas velocity of radon to match the actual radon constellations and simulated radon constellations. So, but based on the references previously, the research is some areas is very rapid, even though the subsurface, for example, just one day, 1 kilometer, the movement was occurred or observed. But the usual case, the gas velocity is very small. For examples of my slide. The usual case, such value are applied to radon concentrations, radon analysis, just here, 10 minus 5 the meter per second. So it means just 10 micrometer per second. So it means just a few centimeter in one day, or a few or 10 centimeter one day. But we believe that when the active areas, gassing areas, humoral areas, this value may be multiplied by 100 over 10, 1,100. So I think that some cases the radon move, for example, several meter or more, 100 meters in the volcanic areas, because of the degassing. And this third question. And the second question, from sun detection radon, how dense is the data? For the MT survey in volcanic areas, we set about 30 the MT data stations, and the interval between the nearby the data point is several hundred meters, so 0.5 or 6 kilometer. So more details, we publish the papers in Applied Geophysics, Journal of Applied Physics in Elsevier 2016. And just a moment. My cell phone. Just a minute. Sorry. Next question. How many? Yeah, it depends on the how size is the reservoir, geothermal reservoirs. Of course, we want to know we wish to know the very details, the structures of reservoir. There may be intervals 50 meters or 500 meters is preferable for the MT survey. So more details about the MT survey, how to be applied for geothermal reservoir, that will be given by my colleague, Professor Goto, maybe tomorrow lecture. So please look forward to hearing Goto Sensei do the lectures. So next question is just a moment. Thank you very much. This simulation is here, related to the advective, the diffusive equations. And the more details about these equations and the numerical simulations, I published the papers in 2009. This paper. Journal, Springer Journal, Environmental Geology. Now, journal has been changed to Environmental Earth Sciences, but published papers. If you're interested, please see my papers. Okay, thank you very much. Very good. 3 questions. And more we have more chat. Just a moment.
Yeah, we have 2 more questions from Ka.
Chat, just a moment. I search chat. How to measure airborne radiometric, how precise is the data? I'm not sure, but because I don't have any experience of airborne gamma ray, airborne radon survey, but the airborne the radiometric survey is common for the areas of the very difficult accessible areas. So there are many papers. The one example is the helicopter, the carry out the very large gamma ray sensor using the 5 or 10. This is the sensor made by NAI, sodium I. I'm sorry, I forgot to say in English, but the chemical name is NAI. So the crystal of NAI is very huge, like that. So this several NAI crystal located in the helicopter, and the way the movement helicopter gamma ray intensities that can measure along the flight line. So, and precise data. It depends on the height of helicopter. Of course, the height is low. The mapping of gamma ray intensities must be precise. But of course, the survey areas they're quite small. With the increase of the height from the ground surface, of course, we can measure wide areas, but the spatial resolutions, of course, decrease. Next one is apart from granitic specimen, these rocks that can be used to measure any oxygen composite test. Of course. So this is because the granitic rocks show the good response of radon constellations due to fracturing and compression test. That's why we used the granitic rocks. But if you use, for example, basaltic rocks or other andesitic rocks, maybe such a change is small. So it is maybe difficult to find out the response between fracturing and radon constellations. So I recommend you to use rocks containing the much radioactive nuclide if you are interested in such a rock testing. Thank you very much.
Okay, thank you very much, Sensei, for the explanation. But because of the time duration, we have to end our class. And before we end the class, maybe have you some closing remarks for this class?
So, voices maybe stopped. Could you say again?
Maybe have you any closing remarks for this class?
Closing remarks. Okay. Well, thank you very much for attending my lectures. Yeah, time is limited. Just 2 hours, and I include several topics, but not all the materials for the radon survey. If you are interested in my lectures and you want to know more details about my papers, if you contact me or if you contact ITB professors, I can send you the references or papers or my papers that relate to these classes. So if you have any questions, please contact me or ITB, your supervisors.
Okay. Thank you so much, Decay Sensei.
Thank you very much.
It's nice to have you here. Maybe before we end the class, can we take a picture together?
Oh, okay.
Miss Riva or Miss Harmita, could you help us to take a picture, please? Say maybe I will close the screen. Okay. Okay, Miss Riva or Miss Harmita? Yeah.
Okay. Get my voice clearly?
Yeah. You might start.
Together. First page. Okay, now is second page. Keep your smile. And it's the last page. Okay, done, Mr.
Okay. Thank you so much, Taike Sensei. Hopefully we can meet in another occasion. And
Okay. Yeah,
Mr. Wahyudi, have you any remarks from you?
Yeah. On behalf of our Department of Geophysical Engineering, we thank you very much for your lecture, Professor Koike, and we hope we can meet again in the next chance. Maybe.
Yeah, I hope so.
Okay. Yeah. Okay. Thank you very much.
Thank you.
Thank you very much.
Thank you. Thank you for very much kind attention.
You're welcome.
Thank you.
Okay, for the all participants, you might leave the room if you.
Okay, I end meeting now.
Oh, okay. Thank you very much.
Okay, thank you very much.
Bye.
Again, Professor Koike. Thank you very much, Dr. Indra Kwan, and thank you for all attendance. We meet again this evening with the lecture from Professor Wayan Senghara about slope stability analysis. Okay, thank you very much and see you later.